Welcome once again in the class of topology. We have started recently the chapter of compact spaces and it is the second lecture on compact spaces. So we are going to have some more theorems, some more results on compact spaces. So the first one I am going to take is theorem: a topological space X top is compact if and only if every basic open cover has a finite subcover. This theorem is also known as Alexander subbase lemma. Alexander subbase lemma. So we are going to prove this Alexander subbase lemma. For the proof, one thing we have to concentrate on is that here we are having if and only if, so the direct proof is necessary as well as the converse part is needed to be proved. So first of all, I am taking the direct proof. So let X top be a compact space. Now what we are to prove? We are to prove that every basic open cover has a finite subcover. We know that the definition of compact space, it states that every open cover has a finite subcover. When every open cover is having a finite subcover, why not basic open cover? It is also an open cover. Since every open cover has a finite subcover, basic open cover must also have a finite subcover. So direct part is obvious, is very much clear in the one step. Now we are going on to the converse part. Let every basic open cover has a finite subcover. This condition is given now. What we are to show that the space is compact. That means we will have to show that not only basic open cover, in fact every open cover is having a finite subcover. So we are taking an arbitrary open cover. So let C containing GIs, where I belonging to a particular family lambda, be an arbitrary open cover of X. Now C is open cover. That means every member of C is top open. So that means every GI is top open. This means GI is top open for every I belonging to the family lambda. On the other hand, if B is base, if B is a base for top, if B is a base for top, then we know that every open cover can be expressed as union of members of B. So every GI is union of members of B. So that means G1 is a union of members of B, G2 is a union of members of B, G3 is a union of members of B. If C is a open cover of X, that means X is union of GI, I belonging to lambda. But every GI is union of members of B. That means in totality you can say that the base is also an open cover, or you can say the members which contribute to some GI, they will form if an open cover for the topology, for the compact, for the space X. So this means you can say, this means we can say BIs such that GI is union of BI belonging to B form form an open cover for X. Here I have left some space. Why? Because it is an open cover, no doubt, but since every member of it belongs to a base, so it is a basic open cover. So it forms a basic open cover for X. But we are given that every basic open cover has a finite subcover. That means this open cover will also be having some finite subcover. So, let B1, B2, B3, Bn, let this be the finite subcover of basic open cover, that I was talking here Bi. This collection of members of base, this was an open cover, and since every basic open cover is having a finite subcover, it must have a finite subcover. Now the next thing is that Gi is union of Bi's. That means every Bi is contained in some Gi. So that means B1 is contained in some G1, B2 is contained in some G2, B3 is contained in some G3, and so on. Bn is also contained in some Gn. Since these B1, B2, B3, Bn, they cover X, that means X is union of Bi's, I vary from 1 to n. And since each Bi is contained in some Gi, so union of Bi's in fact is a subset of union of Gi, I vary from 1 to n. But we need not to put subset here, we can put equal to. Why? Because X is the whole space. If X is contained in some set, that set is also contained in X, so they will be equal. Now we have taken an open cover C and we have obtained a finite subcover. Which finite subcover I am talking about? I am talking about this finite subcover consisting of G1, G2, G3 and so on Gn. This is a finite subcover of C. I have taken an arbitrary open cover and I have obtained a finite subcover of that cover. That means the space is compact. So Alexander's subbase lemma is proved. That means a topological space is compact if and only if every basic open cover of X has a finite subcover. This was Alexander's subbase lemma. And now I am going to move on to the next theorem. Next theorem is write down the statement first. Prove that a Hausdorff compact space is T3. This result we are going to prove now. So prove. One thing is clear. What we are going to prove, we must be clear in our mind. We want to prove it to be T3. And T3 means regular and T1. So we will have to prove that it is regular and it is T1. But we need not to prove T1. Why? Because it is given to be Hausdorff. Hausdorff means T2. And we know that every T2 space is T1 space. So it is already T1. What we need to prove is that it is regular. If it is regular, then because of it is Hausdorffness, it is already T1. So regular plus T1 will make it a T3 space. So what we have to prove now, that if a space is Hausdorff and is compact, then it is regular. That is sufficient to prove it that it is T3. So let X top be a T2 compact space. So it is a T2 compact space and we have to show that it is regular. To show that it is regular, what we have to do? We have to take a closed set B and an element X that does not belong to that particular closed set B, and then we will have to find a pair of disjoint open sets, one containing X and other containing the set B. So let B be a closed subset of X and let X be an element not belonging to B. Take one element Y from B. For every Y belonging to B, definitely X is not equal to Y. Why? Because X does not belong to B and Y belongs to B. So how X and Y can be equal? So X and Y are not equal. And the space is Hausdorff. In a Hausdorff space, if you are having two elements not equal, then always there exists a pair of disjoint open sets, one containing X and other containing Y. So therefore, there exist open sets G and H. You can name it as GY and HY. There exist open sets GY and HY such that your X belongs to GY and your Y belongs to HY. GY intersection HY is phi. Now, what to do? Collect all these HYs. Collect all such HYs. So consider the collection C of all HYs where Y belongs to B. Since we are having HY for every Y belonging to B, that means union of HY will cover B. And since every HY is an open set, that means it will form an open cover. So this means HY is an open cover of B. But what was B? B was a closed set. And we know that closed subset of a Hausdorff compact space is compact. So that means B is compact. B is compact, and here we are having not HY but it is C. B is compact and we are having an open cover for B. So it must have a finite subcover. So therefore C must have a finite subcover. Say HY1, HY2, HY3 and HYN. So I'm naming it as C star. So there must be a finite subcover of C. So this finite subcover, what is the role of the finite subcover? It is sufficient to cover the set B. So this means union of HYI's where I vary from 1 to n, it covers B. It covers B. And union of open sets is an open set. So I can name it as H. So that means H is an open set. An open set H covers B. On the other hand, corresponding to each Y, HY, there will be some GY. So corresponding to HY1, there will be GY1. Corresponding to HY2, there will be GY2. Corresponding to HY3, there will be GY3. Corresponding to HYN, there will be GYN. So I am intersecting all those sets. G is the intersection of GYI's where I vary from 1 to n. And it is a finite intersection of open sets. And we know that finite intersection of open sets is also an open set. So that means G is an open set. And since X belongs to GY for every Y, that means X is in GY1, X is in GY2, X is in GY3 and so on. X is in GYN. So X must be there in G also. So that means X belongs to G. You have taken a closed set B and an element X not belonging to B. You have obtained an open set H containing B, an open set G containing X. Now what else is needed to be proved is that H intersection G is phi. That is the last. If H and G are disjoint, then we have obtained a pair of disjoint open sets, one containing B and other containing X, and that will make the space regular. Already it is T1, so T1 plus regular, it will make the space to be T3. Now we claim that we claim that H intersection G is 5. Suppose not. Let there be some element Z in H intersection G. That means X is in H and X is in G. So it means Z belongs to H and Z belongs to G. H. What is H? H is union of H, Y, I's. I vary from 1 to N. What is Z as G here? G is intersection of G, Y, I's. I vary from 1 to N. If Z is in the union of H, Y, I's, definitely Z will be in some particular H, Y, I, at least in one. So let Z belong to H, Y, J, some particular member of this union. And Z belongs to intersection, that means Z belongs to every G, Y, I. So if Z is in every G, Y, I, that means Z is in G, Y, J also. Z is in H, Y, J, Z is in G, Y, J. This means H, Y, J intersection G, Y, J is not 5, which is a contradiction. Why? Because H, Y intersection G, Y is always 5. That means H, Y, 1 intersection G, Y, 1, 5. H, Y, 2 intersection G, Y, 2, 5. H, Y, 3 intersection G, Y, 3, 5. So H, Y, J intersection G, Y, J is also 5. But it is coming out to be non-empty, which is a contradiction. And this is a contradiction because our supposition was wrong. And what we have supposed? We have supposed that H intersection G contains some element. So that means H intersection G will be an empty set. So H and G are disjoint. We have started with a closed set B and an element X not belonging to B. And now we have obtained a pair of disjoint open sets H and G, one containing B and other containing X, which makes the space regular. Already the space is T1 because it is T2. So regular plus T1, that means the space is T3. So the theorem is complete. That means every Hausdorff compact space is a T3 space. So I'm moving on to the next theorem now. Next theorem, I'm going to write the statement first. A compact T2 space is a T4 space. So it is a theorem almost similar to the previous one. Earlier we have proved that a compact T2 space is T3, and now we are proving that a compact T2 space is T4. Once again, we have to prove that it is T4. That means we have to prove that it is normal as well as T1. But we don't need to prove it to be T1. Why? Because it is T2 and T2 already implies T1. So since it is Hausdorff, it is a T2 space, it is already T1. We have proved it in the chapter of separation axioms that every T2 space is T1. So it is T1. Now, what else is required to prove that it is a normal space? What else is required to prove that it is a normal space? To prove it a normal space, we have to start by taking a pair of disjoint closed sets. So let A, B be disjoint closed sets. That means A and B are closed and A intersection B is 5. If you take some element X from B and some element Y from A, then X is not equal to Y, because if X is equal to Y, then A intersection B is not 5, but A intersection B is given to be 5. That means an element from B and an element from A, they cannot be equal. Now forget about this, that Y belongs to A. Forget about this. You just take that X belongs to B. B is a closed set. There is an element Y such that X is not equal to Y, and then concentrate on the proof of the previous theorem. There also we have a closed set. We have taken element X from B and an element Y such that X is not equal to Y. And what we have obtained? We have obtained a pair of a disjoint open set, one containing B and other containing other containing Y. So here again, X not x belonging to B and y does not belong to B. Here y does not belong to B because y belongs to A. So what we have obtained, so by the proof of the previous theorem, there exists this joint open sets, I am naming them as GY and HY, such that Y belongs to GY, your B is a subset of HY, and GY intersection HY is phi. This result is by the proof of the previous theorem. Now repeat the proof of the previous theorem, almost the repetition. What we have to do now, this Y belongs to GY, so and Y is an element of A. So what you have to do, collect all these GYIs. So GY, where Y belongs to A, collect all these and name it as C. So what it will be? It will be an open cover of A, because for every element of A you are having one open set. So the totality of these open sets will contain A. So it will be an open cover of A. And what is A? A is a closed subset of a compact Hausdorff space, and we know that closed subset of a compact Hausdorff space is also compact, so it is also compact. And corresponding to each GY there is HY, and it is a open cover of a compact space. And if you are having open cover of a compact space, definitely there will be a finite subcover. So let C star is equal to GY1, GY2, GYN be finite subcover of C. Finite subcover of C. Why it exists? Because your A is compact. Now, corresponding to each GY there is some HY. So corresponding to GY1 there will be HY1. Corresponding to GY2 there will be HY2. Corresponding to GYN there will be HYN. Now, union of these GYIs, I vary from 1 to n, let it be G. It will definitely cover A because it is an open cover of C, and C, so it is a finite subcover of C, and C was open cover of A. So finite subcover, the members of finite subcover will cover A. So G contains A, that means A is a subset of G, and each GYI, GY1, GY2, GY3, GYN, each GYI is an open set. So their union is also an open set. So A is contained in an open set. On the other side, B is a subset of HY. So for every Y, so that means B is a subset of HY1, B is a subset of HY2, B is a subset of HY3, B is a subset of HYN. If B is a subset of each of HY, that means B is a subset of intersection of HYI. I vary from 1 to n. These HYIs are nothing but each YI is the corresponding open set to GYI. And since each HYI is open, so finite intersection of open sets is open, that means this set, let it be H. So this H is also open. G is an open set and it contains A. H is an open set, it contains B. A and B we have taken in the starting a pair of disjoint closed sets, and now we have obtained a pair of open sets, one containing A, other containing B. What remains to prove is that G intersection H is phi, and the proof is almost similar to the previous theorem once again. So suppose we are going to prove that claim that G intersection H is phi. Let Z be some member of G intersection H. That means Z belongs to G and Z belongs to H. So this means Z belongs to union of GYI, I vary from 1 to n, and Z belongs to intersection of HYI, I vary from 1 to n. Since Z is in the union of GYIs, Z will definitely be in some particular GYI. So let Z be in GYK for some K belonging to the set 1, 2, 3 up to n. It may be gy1, it may be gy2, it may be gyn. And z is in every hyi, so definitely z is in hyk also. Now z is in gyk, z is in hyk, that means z belongs to the intersection of gyk and hyk. So z belongs to gyk intersection hyk. And this means gyk intersection hyk is not phi, and this is again a contradiction because intersection of every gy and every corresponding hy is always phi. So gyk intersection hyk cannot be non-empty, it must be empty. So that means we have arrived at some contradiction, and this is the contradiction because our supposition was wrong, and our supposition was that G intersection H is not phi, so it must be phi. So now from where we have started? We have started by taking a pair of disjoint closed sets A and B, and we have obtained a pair of disjoint open sets G and H such that A is contained in G, B is contained in H, and G intersection H is phi, which makes the space normal. The space was already T1 because of its Hausdorffness, so that means the space is normal as well as T1, which makes the space T4. So we have proved that every compact Hausdorff space is normal. So here I am going to stop this video. In the next video we will have more and more theorems on compactness. Thank you once again.